So we're starting our homework group associated with optimization. And our first problem is my cursor's not coming up. So hopefully it'll come here in a second. Oh, there we go. Okay, so we're starting on problem number 6. And these are these word problems that, well, they're all word problems, but this is the one that just involves a number statement. So I'm going to read it and then I'm going to write out what the, so basically have a primary equation and a secondary equation. And the first thing you want to do is define your variables. So you've got x is your first number, and y is your second number. And they're asking for the sum. Okay, what are we going to do? I want to minimize the sum. The sum is minimized. So let's say S is the sum of the two numbers. So we're trying to maximize it. So our primary equation is S is equal to X plus Y. We're trying to maximize or minimize the sum. Make sure we're in the right problem here. Sum is a minimum. Okay, and then you have a secondary equation. And the secondary equation allows you to rewrite the primary equation in terms of one variable. Because we can only take right now we can only take the derivative of a function with respect to one variable. And so we have two variables, x and y. So the secondary thing is to link them. And it says the second number, which is the let's see, the second number is the reciprocal of the first number. So the second number is equal to the reciprocal of the first number. So that's my secondary equation. And what else do we know? Well, it's really nothing. That's it. Okay, what is the domain? Well, positive numbers. So the domain in this case is that x has to be greater than 0. And y has to be greater than 0. So if we end up with a solution where x or y is negative, then that's not one of our solutions. We're only going to look at those particular solutions. So we take the secondary equation, we plug that into the primary equation. So for x, we'll put in, for y, we'll put in 1 over x. It doesn't really matter which one we solve for first. You just have to solve for one or the other. So I could solve, the other option is x is 1 over y. And so I could make either two of those substitutions, and you'll get the same answer either way. So I've made the substitution. Now the original equation is only a function of one variable. So then it says use the methods from section 3.1 through 3.4 to find out what are the minimum values for x. And are the minimum values for what values of x give you a minimum value for the sum. So what we do is we take the derivative ds dx, because x is our variable. So on the left-hand side, we get ds dx equals 0. On the right-hand side, we'll get 1 minus 1 over x squared. How do we get that? Well, this is the same as x plus x to the minus 1. So when you take the derivative of that, you'll get negative 1 times x to the minus 2, which is that. You set that equal to 0. Because to minimize or maximize something, you're looking for the critical numbers. So then if you take this equation, multiply by x squared, you'll get x squared minus 1 equals 0. Because 1 times x squared is x squared. 1 over x squared times x squared is 1, negative 1, or 1 over x squared times x squared is 1, and 0 times x squared is 0. So we solve there, we get our solution is x is equal to plus or minus 1. Plus or minus the square root of 1, which is 1. So those are our two numerical solutions, but x equals 1 is the only solution in the domain. The domain as we have defined it, or the problem has defined it. So once you have that, then you can go back to the secondary equation. Secondary equation said y equals 1 over x, and all you have to do is plug in the determined value of x, and you get 1. So the answer is x equals 1, y equals 1 are the two values for x and y where the sum is a minimum. So let's just try a value different than that. Let's say x is equal to 2. Well, y would be equal to 1/2, and then if you add the 2, x plus y is equal to 2.5, which is greater than 1, or greater than 2. You know, our sum here, x plus y equals 1 plus 1, which is 2. So you can see I picked something other than this. I picked x, y was fixed because of that, and you see it's 2.5. If I did x equals 3, y would be equal to 1/3, and so when you add those two together, x plus y, the sum is 3 1/3, which is also greater than 1. And if you did something like x equals 1/2, y would be equal to 2, and when you add those two together, you get 2.5, which is again greater than 2. So I mean greater than 2. These all are greater than 2. So you can see, just I checked it by just picking some numbers other than that, and you can see how it works out that this is a minimum. Now the question is it a minimum or maximum? We don't really know that until we apply some other tests. So let's go ahead and do that. Because where the first derivative is 0, it can be either minimum or maximum. So how would we know that besides me plugging in numbers to show that it is a minimum? Well, you can take the second derivative. So ds dx was equal to 1 minus 1 over x squared. So if we take the second derivative, d squared s dx squared, that's going to be 0. And we're going to have 1 x to the minus 2, so that'll be plus 2, because you'll have negative 2 times negative 1 is positive 2. And then you'll have it x to the minus 3 power, which will be 1 over x cubed. And you can see that if x is greater than 0, which is what it is in this domain, then d squared s dx squared is greater than 0. So if this is positive, if we divide by a positive number, it'll still be positive. So it's always positive. So what does that mean? It means that it's concave up, which means it looks like that, which looks like a minimum. So that's how you would use the second derivative test to determine that. Okay, we're problem number 7. So it's another one of these word problems. So keep your book open. It says, so what we need is to define the variables. So we're going to call the first, just like we did last time in problem 6, the first number we'll call the variable x. We'll call the second number y. And let's see what else they're asking. And the product, so we'll call the product of the two, we'll call that p. So there's our variables. Next, what we do is we write the primary equation. And the primary equation is the one we want to minimize or maximize. So it says the product is a maximum. So product means we multiply two things together. So p, which is the product, is equal to x times y. So that's our primary equation. We're trying to minimize or maximize the product. So we have two variables though, so again we need a secondary equation to rewrite the primary equation in terms of one variable. So the secondary equation says that the sum of the first, so we take the first and twice the second, is equal to 100. So that's our equation. That's our secondary equation. So we need to solve either this secondary equation either for x or y. And since we have 2y, it's probably easier to just solve for x. So solve secondary equation for, in this case, x. Could be either x or y. So you get x is equal to 100 minus 2y. And then you substitute into the primary equation. So we get p is equal to x, which is 100 minus 2y times y. Now let's think about the domain. What's the domain of this thing? Well, x has to be greater than 0 and y has to be greater than 0. Also, if the product is 100, is there anything there, or no, the product is maximizing. So if the sum of the two numbers equals 100, then we know that x has to be less than 100, because if we had x greater than 100, then y would have to be negative, so that's not going to work out. And we also know that y has to be less than 50 for the same reason. If we took 2 times y, that would give us 100. Anything greater than 50, I guess it could be less than or equal to, I think. Actually, not less than or equal to. It can't be equal to because that would make one of the others 0, and it says it has to be a positive number. So I guess the question is 0 a positive number or not? And I don't think it is. So okay, so that's our domain. So when we find our solution, when we maximize this, maximize or minimize this, whichever one they're asking for a maximum, then we would our solution would have to be in the domain, and that we set here. And also, what else? I think that's it. Oh, we also might check the endpoints, because they're asking for the absolute, basically they're asking for the absolute extrema. So we also should really consider the endpoints. We might be able to show that those don't make any sense, so we might not even have to do the endpoints. And one endpoint would be 0, so that's probably not going to work out. Okay, but we'll show it. We'll do it. Okay, so now what we do is we take the derivative of the primary equation with respect to the variable. And before we do that, though, let's multiply this out. So we have 100y minus 2y squared. That way we don't have to use the product rule. So the derivative of 100y with respect to y is just 100 times 1. The derivative of y with respect to y is 1. So we get 100 minus 4y. Okay, the minimums or maximums are going to occur, if there are local minimums and maximums, they occur at the case where either the function is equal to, the derivative of the function is equal to 0, or the derivative of the function is undefined. In this case, this is always defined, so all we have to do is do the first one. So you get negative 4y is equal to negative 100, divide by negative 4, and you get 25. Is that in our domain? Yes. Okay, now, so that's the y part. So to find x, use the secondary equation. So the secondary equation was this one. So all I have to do is say x is equal to 100 minus 2 times y, which is 25. And so x is equal to 50. Is that in the domain? Yes. So again, this could either be a minimum or maximum. So what we would do is to find, we'd use the second derivative test. And what that means is we take the second derivative of p with respect to y, and that's just equal to -4. So therefore, second derivative is negative. What that means is concave down, which means maximum. So we know it is a maximum at that particular point. If you went to the other extremes, you would see that it wouldn't work, because if one of those is 0 and the other one's the maximum, you're going to get 0, and you'd end up with a product that's 0, which is less than what we got earlier. So that's another way of looking at the endpoints. Okay, let's see what problem we're on. 14. Okay, so the next two problems are ones that relate to graphs. So let's see if we can draw what's going on here. And we could probably actually get the answer just by drawing the picture, but we will try to, we'll still do it analytically. So this will be the function, the square root of x minus 8, and this would be x equals 8. So the domain would be x greater than 8, greater than or equal to 8. Square root function looks like this, and this just is offset by 8 units in the x direction. And then you have point 2 comma 0, which is this point. So the question is, find the point on the graph of the function that is closest to the given point. And so let's just put it on here. Well, obviously the answer is going to be right at this point, but let's prove that's true. So this is point x comma y. This is point 2 comma 0. And so, just like in the book, you look at the, actually we did one like this in class. The primary equation is d, which is the distance, is equal to the square root of x minus, we'll call it x1 squared, plus y minus y1 squared. So you're basically using the Pythagorean theorem. Again, it's amazing how many times we use that. So we're looking for the hypotenuse of the triangle. This side of the triangle is the difference between x and our initial point. And the y value, the y difference here, over this side of the right triangle, is going to be y minus y1. And so you square them, add them together, and take the square root, and that gives you the hypotenuse. Of course, this is a function of both x and y, so what we're going to do is we're going to substitute. Well, before we do that, though, we will put in x1 and y1. So x1 is 2, and y1 is 0. Okay, so that's a primary equation. The secondary equation is y is equal to the square root of x minus 8. So we can make that substitution. So for y, we put in x square root of x minus 8, and we square it. We subtract 0, so that's in there. So now it's only a function of x. So we could take the derivative of this whole thing, but when you maximize the square root, you're also maximizing. If you maximize the argument, meaning this thing inside the square root, you're also maximizing the square root. So, you know, if A is greater than B, then the square root of A is greater than the square root of B. Is there any case where that's not true? Well, yeah, if A was less than 1, but in this case it's not the case. So we can do that. So we really don't have to, what we can do is let's maximize what's in the argument, and that makes the derivative a lot easier. And rather than taking this derivative, let's just multiply it out. So this you FOIL, you'll get x squared minus 4x plus 4, and then when you square that, you'll get x minus 8. Square root of x minus 8 squared is just x minus 8. So we simplify x squared minus 3x minus 4. So that is now the primary equation. What is the domain of x and y? So x has to be greater than 8, and y has to be greater than 0. That's about it. If we go back to the original picture here, x is 0 to infinity, and y is from, pardon me, x is from 8 to infinity, and y is from 0 to infinity, which is what we're saying here, and actually equal to. So now we're going to take ds dx. So you take the derivative with respect to x, and you get 2x minus 3. And we set that equal to 0 and solve for x. And so you get x is equal to 3/2. And they say, oh, that's the maximum minimums at 3/2. But not so quick. This is not in the domain. So we don't use that. So that's not working. So then you look at the then you're going to look at the beginning and the end of the domain. So if you look at x equals 8, and at x equals 8, y equals 0, if you plug that into here, the distance is going to then d is going to be equal to the square root of 8 minus 2 squared plus 0 minus 0 squared. And so you get that is equal to square root of 6 squared, which is 6. And so that's why, if we go back to the original question, this is a minimum distance. It's right here, because anytime we move to the right on this graph, it's just going to get larger and larger and larger. So there is no maximum distance. There's a minimum distance, which in this case turns out to be at the end of the domain. There's no local minimum or maximum in this particular case. Okay, so we're now on problem 16, which is the next one that involves a function. So it's basically the same procedure that we just did in 14 if you've looked at that one. In this case, we actually do get an answer that's we do get an actual minimum distance. So this is x, this is y. So what does this look like? Well, remember, this is going to shift the quadratic equation, the quadratic function to the left one. You always take the negative of that, so it's going to look something like this. So it looks like that, it comes down like that, and then you've got 0.5, 3, which is going to be out here. and then you look for the minimum distance. So you can see if I go here, it's going to be value, then it gets smaller and smaller and smaller, and then it gets this closest distance, and then it gets longer again. So it's going to be somewhere in here. So what do? We write our primary equation. The distance between 2 points is going to be x minus x1 squared plus y minus y1 squared. This is a function of 2. Also, like in the previous problem, we're going to take the square root off because we don't need that. So we're going to say s is just the square of that. So this is my primary equation. And we need a secondary equation to rewrite the primary equation in terms of one variable. So the secondary equation is y is equal to x plus 1 squared. So, and also we have x1 is equal to 5 and y1 is equal to 3. So let's make both of those substitutions into that equation. So you get x minus 5 squared plus y, but y is equal to x plus 1 squared, and we subtract 3, and we square it. X minus 5 squared plus y is x plus 1 quantity squared minus 3. So we're just going to have to multiply all this stuff out. It's probably the easiest thing to do. So we'll get x squared minus 10x plus 25 from the first thing. The second part we're going to have to do in 2 steps. So if you multiply that out, you'll get x squared plus 2x, and then you'll have 1 times 1, which is 1, and then you'll subtract 3 from that, so we get negative 2, and we square that whole thing. So what that was x squared plus 2x plus 1 minus 3, which gives me negative 2. Okay, now let's just do this one on the side, so we're going to take that and we're going to square it, which means multiplying by the same thing. So the way you do this, it's not FOIL, it's kind of like FOIL, but we may multiply this times each term, and then we multiply this by each term, and then we multiply that by each term. So we're going to end up with 9 terms. So the first one, you'll end up with x to the 4th, x to the 4th plus 2x cubed minus 2x squared. Okay, that's this times each one of those. And then we go to the next one. So you get plus 2x cubed plus 4x squared minus 4x. So that's this times each one of those. And then finally, you'll get negative 2x squared minus 4x plus 4. Okay. So that's what s is equal to. Well, not actually s, it's just part of s. So let's simplify that. So we get x to the 4th plus 4x cubed. 2 plus 2 is 4. Negative 2 plus 4 minus 2 is 0. So we get 0x squared. And then we have the x's, which is going to be negative 8x plus 4. So let's put all that together into this equation. So we have x squared minus 10x plus 25 plus this part, which is plus x to the 4th plus 4x cubed minus 8x plus 4. And then we simplify it by combining like terms. So we get x to the 4th plus 4x cubed and plus x squared. And then we have minus 10 minus 8. So that's negative 18x and then 25 plus 4 is 29. Okay, so that's the primary equation, only in terms of x. So now we take the derivative. Let's look at the domain. So x, this is point xy. So x can be any number, and y has to be greater than 0. So we'll write that up here. Domain x is all real numbers, and y has to be greater than or equal to 0. So then we take the derivative. You get 4x cubed plus 12x squared plus 1 minus 1x, or 2x, sorry. 4x cubed, 12x squared plus 2x minus 18. And we set that equal to 0. And, okay, let's divide by 2, so you get 2x cubed plus 6x squared plus x minus 9 equals 0. So we need to find the roots of that equation. And those will be the solutions where the derivative is equal to 0. So let's use a little common sense here. Let's look at our graph. So what we're looking for is x value. So x equals 5. So I would think it's going to be either positive 1 or positive 2 if it's going to be a nice even number. So let's try that and see what happens. And we'll use synthetic division for that. So we're going to try x equals 1 and x equals 2. So we're going to write our coefficients 2, 6, 1, negative 9. And when we do this, we put in the x value, not the factor. You know, the factor would be x minus 1 and x minus 2. So I'm going to put in 1, see what happens. Okay, bring 2 down. 2 times 1 is 2. That's 8. 8. 1 plus 8 is 9. 1 times 9 is 9. You get 0. So that is one of the solutions. So x equals 1 is where ds dx, I don't know why I put ds dt, ds dx equals 0. Let's just try, well, we don't have to try 2. We already 2 work. Let's just put it in there just to see what happens. You'll see it doesn't work. So you bring 2 down. 2 times 2 is 4. 6 plus 4 is 10. 2 times 10 is 20. 21. 2 times 21 is 42, and you get positive 33. Of course, so that's not a solution. So there you go. That's our solution. So what that says is we have a critical number at x equals 1. So that could be a minimum or maximum. Now, of course, we know that's a minimum just from the drawing. But let's prove it by using the second derivative test. So ds dt was equal to, well, actually it was twice this. It was 4x cubed plus 6x squared plus 12x squared plus 2x minus 9. Is that correct? 4x squared, 4, 12 to negative 18. No, negative 18. Yeah, I forgot to multiply that by 2. Okay, so that was the first derivative. So we take the second derivative, and I did it with respect to t again. I don't know why I keep doing that. my physics. Okay, so we now take the derivative. So you get 12x squared plus 24x plus 2. 12x squared, 24x, 2. Okay, now the question is the second derivative greater than 0 or less than 0 at x equals 1? So we plug x equals 1 in there, and you can see almost immediately is that it's positive, because all these are positive and you're putting a positive number in. So you get 12 plus 24 plus 2, which would be 38, which is positive. Okay, so positive second derivative Now what that means, concave up means that, which means therefore we have a minimum distance at x equals 1. And let's actually, let's plot this thing just to show you that it's true. I'll need to bring the graphing program up, which I don't have up right now. So let me share the graphing program with you. Okay, and actually what I'm going to do is I'm going to bring the graph back. So let's go ahead and put it in there. So the function was x plus 1 squared. And let's graph it. And I'm going to change this so that so we get squares. So I forget which way we go here. Yeah, there we go. So you can see it's almost, these are squares, so that makes it easier to do this. And we'll go back and get the camera and copy that. And I just switch back. Okay, there's our graph. Let's put it on one page so we can see better. So the x value was 5, 3. So let's put that on there. 5, 3. And what it said was that the minimum distance between this red curve and this point occurs at x equals 1. And if you go up, that is equal to y equals 4. And if we draw a straight line between this point and that point, that distance is going to be a minimum. And one thing you'll also notice is that this is a right angle. It's not a coincidence. So the minimum distance between a curve and a point is going to be at a 90-degree angle between the 2 points. Okay, now we're moving on to problem 19. Now this involves an area. So 19. So let's read the problem. A farmer plans to fence a rectangular pasture area adjacent to a river. So here's the river, and here is the pasture. So it's going to be going out from the river, and it goes along the river, and then back to the river. The pasture must contain 18,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Okay, so let's define some variables. We'll say this distance is x and this distance is y. Now let's change it the other way around just because we always like to have y. vertical direction. So this is y, this is y, this is x. So what we're trying to do is minimize the, what does it say? Pasture must contain what dimensions would require the least amount of fencing. So we'll say L is the length of fencing. So this is my primary equation. Might be tempted to use area as the primary equation, but that's not right. Okay, so the length is going to be equal to 2y plus x. So this is because this side doesn't need fencing. If you had just a rectangular area, a fenced-in area, and without a river, then you would have to, it would be 2y plus x, 2x, but it's not. Okay, so that's my primary equation. My secondary equation, and sometimes they call the secondary equation, say it is the, it's the way it's called, it provides a constraint to the problem. So our constraint in this particular case is that the area has to be 180,000 square meters. So we can say the area is 180,000 square meters, and the definition, the equation for area is height times width, x times y. So that's our secondary equation. Now, what are our limits on y and x? Is there a limit on y and x? Well, x has to be greater than 0 and y has to be greater than 0. So we can't have negative lengths. That's about it. So that's our domain. Mathematically, we could have negative numbers, but physically we can't have negative areas, so that's not going to work. Because if you had two negative numbers, that would give you a positive number. Okay, so now what we do is we're going to use the secondary equation so that we can rewrite the primary equation in terms of one variable. So we'll take the secondary equation and solve for one of them. It doesn't matter which one we solve for. So I've solved for x by dividing by y. So that's that, and then we substitute into the primary equation. So we get L is equal to 2y plus 180,000 divided by y. Okay. So now it's just in terms of y. Take the derivative. And we take it with respect to y, of course, so we take dl dy. So the first term just becomes 2, and the second term, we're going to have 180,000 times the derivative of 1 over y, which is negative 1 over y squared. Why is that? Because I can rewrite this as 180,000 times y to the minus 1 power. So when I take the derivative, I get negative 1 times y to the minus 2 power, which is exactly what we had there. The parentheses to make sure that we know we're multiplying it out. So we set that equal to 0. And so we'll get 2y squared is equal to positive 180,000. They multiplied by y squared, give me that, and then I move that to the other side. So you get y squared is equal to 90,000 by dividing everything by 2. And then you take the square root. So y is equal to plus or minus the square root of 90,000. And what is that? I'm going to show you two ways here. The first way is just stick it in a calculator, and you get 300, plus or minus 300. But the domain says that y equals 300 meters is a solution. Y equals negative 300 is not in the domain, so we don't use that. Okay, the other way, just this is a scientific notation thing. So if you took square root of 90,000, 90,000 is 9 times 10 to the 4th power. So the square root of 9 is 3, and the square root of 10 to the 4th is 10 to the 2nd. So you just take the exponent and divide by 2, and of course that's equal to 300. That's the advantage of, when you do 90,000, you're like, is that like 30 squared, or is it, you have to take the square root of 90? Well, it turns out that, well, let me show you another example. Let's say you have the square root of 900,000. What would happen there? Well, you'd say, oh, well, that's the square root of 9 times 10 to the 5th. And what you would do is say, oh, I can't take half of 5 and get a whole number. So I would rewrite that as 90 times 10 to the 4th, which now I can get a nice even number. So you get the square root of 90 times 10 to the 2nd. And of course, the square root of 90 is not something that's a nice even number. It's you get y is equal to 9.48 times 10 to the 2nd, which would be 948. So that's what happens when you have an odd exponent. You take you increase this by 10 and decrease that by a factor of 10 to balance it out, and then you can do it. That's the way we used to do it on using slide rules. Okay, so that's just for your interest. And then you go, so to find x, use the secondary equation. And because you've already solved that in the process of rewriting it, we can go back. It's just, where was it? Secondary equation solved for, there was the secondary equation. So that was x is equal to 180,000 divided by y. So x equals 180,000 divided by y. X equals 180,000 divided by 300, and you get 600 meters. So we get y equals 300 meters, x equals 600 meters. Again, is this a minimum or a maximum? So min or max. Well, we look at the first derivative, dl dy was equal to, what was it equal to? 2 minus 180,000 over y squared, I think. Let's go back here. 2 minus 180,000 over y squared. Okay, so that was the first derivative. So we take the second derivative. So this goes to 0. This is the same as 2 minus 180,000 y to the minus 2. So what you'll get is negative. So you have a negative sign. You'll get negative 2 times 180,000 divided by, or times y to the minus 3 power. So we get 360,000 over y cubed. So negative times a negative is positive. 2 times 180,000 is 360,000. And since y is greater than 0, d squared L dy squared is positive, is greater than 0, since d squared y dl squared is greater than 0, second derivative is greater than 0, we're concave up, which means we're like that. Therefore, we have a minimum length at x equals 600 meters and y equals to 300 meters. Okay, we are on problem number 20, so it's another fence problem. And so what we have is a corral. It's made up of 2 parts, and they are the same. So we'll just clone that. And so they've already shown us that this is called y, this is called x, which is the distance, these distances. So it says a rancher has 200 feet of fencing with which to enclose the 2 adjacent rectangular corrals. What dimensions should be used so that the enclosed wall area will be a maximum? So the primary equation is the one involving area, because we're trying to maximize that. So area is equal to something. Well, it's going to be x. It's going to be 2 times x times y, because this area is x times y, and there's 2 of them. Then we have a secondary equation. That's so we can rewrite the primary equation in terms of one variable. So the secondary equation is relating to the amount of fencing I have. So we'll call, so the amount of fencing consists of how much we've got. So we got 3y and 4x. So 3y plus 4x is 200. 3y plus 4x equals 200. 1, 2, 3, 1, 2, 3, 4. So now we can solve this secondary equation for x or y, so I'm going to choose x. So we get 50 minus 3/4 y. So then we substitute into the primary equation. So we get a is equal to 2x, x is 50 minus 3/4 y times y. So x is this and y is y. So now we have the primary equation in terms of just y. So let's go ahead and multiply it out completely. So 2 times 50 is 100, and then times y is 100y. So we get 100y, and then we get 6/4. 2 times 3 is 6. 6 divided by 4 is 3/2. So we get minus 3/2 y squared. So that's the area in terms of y. So we take the derivative, dA dy, and we get 100 minus 3y. So you get 2 times 3/2 is 3, and you reduce the exponent by 1. Then you set that equal to 0 and solve for y. So y is 33.33333. 3333. Okay, so that's y. Then you go back to the secondary equation, solve for x. And I just realized we forgot to put in what our limitations were. And this 33 is 100 divided by 3. I did that so I could cancel those out. and you get x is equal to 50 minus 25, which is 25. And what are the units? Feet or meters? Feet. So we get y is equal to 33.33 feet, and x is equal to 25 feet. So those are my solutions. The domain, again, x has to be greater than 0, but less than 200 feet. And the same with y. There's no way that it could be greater than 200 because that's all I've got as far as fencing is concerned. And are these two in those domains? Yeah, well, 33 is and 25 are both in there, so it works out good. You can't have any negatives. And so now what we do is use the second derivative test. To figure out whether the area is a minimum or a maximum. It doesn't actually ask us for what the area is, it just asks us for what the dimensions are. So we can see that right across here, dA dy, the first derivative is 100 minus 3y. So d squared a y squared is equal to negative 3. So the second derivative is negative. That means, therefore, concave down. Therefore, that. Therefore, it's a maximum, which is what we're looking for. So we confirm that it is a maximum. Okay, number 20. So we have this situation. This is 24, what I just said, but whatever I said, I meant this. So here's what the drawing looks like. And we have some rectangle that we're going to create. So let's do the rectangle. So it's going to start here, and then it's going to go down. Create that. So this is point x comma y. This is so this has dimensions x. This has dimensions y, and we're looking for the area of that. And this intersects at 3 and 6. And the equation for the line is y is equal to 6 minus x over 2. So you see it has a y-intercept of 3. When x equals 0, you get 6 over 2, which is 3. And when x equals 0, when y equals 0 is when the numerator is 0. So you get 6 minus 6 is 0. So that's where you get the x-intercept. Okay, now what they're asking for is, says the rectangle is bound by the x and y axis. What length and width should the rectangle have so the area is a maximum? So the primary equation involves area, because that's what we're trying to maximize. So we get area is equal to just x times y. And the secondary equation is just the equation. Y is equal to 6 minus x over 2. Because xy has to be constrained, but it's constrained to be on this thing. So if we were to, if we were to pick another xy, I'm going to pick one that's really small, say here, you can see that area is a lot smaller than this area. And if I did the same thing in this direction, then I have a really small area. So somewhere in here, it's going to maximize what it is. And you probably kind of guess it's going to be something like probably 3 and 1.5 maybe. Don't know exactly. We'll find out. So we have primary equation, secondary equation. What's our domain? Well, x is between 0 and 6, and y is between 0 and 3. Of course, it's not going to be 0 or 3 because then you'd have just this really little sliver, so we know it's going to be somewhere in the middle. So we've already solved for the y, so might as well do that. We might as well plug that into the primary equation. So now let's multiply it out. So you get 3x minus x squared over 2. 6 divided by 2 is 3. X times negative x is negative x squared divided by 2. Okay, so that's the equation, primary equation in terms of one variable. So we take the derivative with respect to x, and we'll get 3 minus x. That's because x derivative of x squared is 2x. 2x divided by 2 is 1x. So that's it. You set it equal to 0 to find minimum. You get x equals 3. And then to find y, you just go back to the secondary equation, which said y is equal to 6 minus x over 2. So we just plug that in. 6 minus 3 over 2, which is 3/2. So our guess was actually correct. These are in the domain, so that's good. And if we want to know whether it's a minimum or maximum, then we take the second derivative, and we get negative 1. So the derivative of 3 is 0, the derivative of x is 1. So we get negative 1. And so since d squared a dx squared is less than 0, then we are always concave down, because it's always negative 1 is always negative, and that means this, which means therefore we have the maximum, which is what we said we could tell. Okay, we got 2 additional problems here that are a little bit more challenging. So 54, we're looking at an offshore oil well, and so let's draw the picture. That's good. So here's our shoreline, and here is a platform, and then we'll put the oil refinery right down there. So the oil well is a distance of 2 kilometers from the shoreline, and the refinery is 4 meters along the coast. So let's write those down. So 2 kilometers, 4 kilometers. It's just laying pipe in the ocean is twice as expensive as on land. So what's going to happen is you're going to have 2 parts. You're going to have a part on the ocean and a part on the land. And there's going to be a length. And so what we need to do is to come up with some kind of, well, what are we trying to do? We're trying to minimize cost. So cost is equal to the cost per length times length. And what we know is that the cost per length for the ocean is twice as expensive. So let's call it CL, cost per length. And we don't actually have to know what that is. We just need to know that the ratio is twice, this value is twice as much on land. So let's just call this L1, and we'll call this L2. So we'll say C is cost. So it's going to be length L1 times 2CL. So CL is cost per length on land. So in the ocean we have L1 plus L2, that's the length on the land, times CL, cost per length on the land. So that's the total cost. Now the question is, we need to get this in terms of one variable. This is our primary equation. So the question is, how do we do that? Well, actually, I think the easier in this case is to actually have two secondary equations. We're going to call this distance here x. So we're going to have a right triangle involving that, and then we can have a right triangle that involves this distance here, I guess. Actually, I don't think we need a right triangle because it's not a way, so we really don't have, only have one right triangle. So let's do part. Okay. So we're going to use a Pythagorean theorem to say that L1 squared is equal to x squared plus 2 squared. So it's this triangle. X squared plus 2 squared is L squared, L1 squared. And we can also say that L2 is equal to 4 minus x. So this whole distance is 4. This is x, so this blue is 4 minus x. And by doing that, having this intermediate quantity, we can solve for x, take dc dx and find x, and then we can plug it back in here to find L1 and L2. And what are they asking for? What path should the pipe follow? So we'll make an x, what's the domain of x? Well, it has to be greater than 0, and it has to be less than square root of 2 squared plus 4 squared. No, actually, that's not true. It'd be 2 plus 4. 2 plus 4. Why is that? Because if we went here 2 and then we went there 4, that would be 6. Oh, sorry. Nope, that's not true. X just has to be less than 4. Because if we went here, we go 2, x would be 0, and that would be 4. If we went straight this way, x would be 4, and this part would be 0. So that's our domain. So let's substitute it in. So x is equal to L1. L1 is equal to the square root. I'm going to take the square root of x squared plus 4 times 2CL. And L2 is 4 minus x times CL. Okay, so now we have the primary equation. This is our primary equation, and we had two secondary equations. Okay, so you take the derivative of that with respect to x. So this, you get 1/2 times x squared plus 4 to the negative 1/2 power, and then you take the derivative of the argument inside because it's a chain rule, and then you multiply by this, which is, these are constants. And the derivative of 4 is 0, and the derivative of x is -1, so we'll get -1 times CL. And we set that equal to 0, so let me rewrite it as, okay, what we can do is, let's just go ahead and simplify while we're doing it. 2 cancels out with 2, so what we get is we get x divided by the square root of x squared plus 4 times 2CL minus CL is equal to 0. So you see we divide by CL, and that's why it doesn't matter, because it cancels out when we do the derivative. So we'll get 2x divided by the square root of x squared plus 4 minus 1 is equal to 0. 2x is equal to the square root of x squared plus 4. How do I get that? Move that to the right-hand side so it becomes positive 1. And then you kind of multiply everything by this, and you get that expression. Okay, now we can square both sides. So we get 4x squared is equal to x squared plus 4. Subtract x squared from both sides. Take the square root. I'll actually solve for x squared 4/3. Take the square root. You get x is equal to plus or minus the square root of 4/3. So we take the positive one of those two because that's in our domain. And let's go ahead and put this in decimal form. So we take the square root of 4 divided by 3, which is 1.15. So 1.15 kilometers. And so then we could go back to our primary equation, our secondary equations, which said that L1 is equal to the square root of x squared plus 4. So L1 is equal to the square root of 1.15 squared plus 4. So we square that, add 4 to the square root. So it's 2.3 kilometers. And L2 is equal to 4 minus x. So we get 4 minus 1.15. And so we get 2.85 kilometers. Yeah, I'm just going to check this out here because since it has some interesting numbers, I don't want to assume I did it correctly. So this is 54. Okay, what does it say here? It says x equals 2 divided by the square root of 3, which is the same as the square root of 4 over 3, so that's correct. Yeah. Okay. So that's right. Okay, well, as you can see, because I'm showing you the whole thing at this point, is I did the problem and I messed up. I'll tell you where I messed up, but this is problem 59, and you're given an equation for the cost as a function of the number of units produced. So what we're going to do is we don't have a secondary equation, we just have an equation. So it's just a matter of taking the derivative of this function with respect to x and finding out the values of x where that derivative goes to 0. So I'm going to rewrite the original equation as 200 times x to the minus 2. And here I have a quotient, and so we're going to use a quotient rule on that. So let's go over a couple of pages because I did it over here. So this is my quotient, x divided by x plus 30. So that's my numerator, that's my denominator. So I take the derivative of each one, which is just going to be 1 in both cases, and then I use the quotient rule. So I take this times that and minus that times that, divided by the denominator squared of the original function. So the x's cancel out. You've got 1 times x, which is plus 1x, and you've got minus x. So this is the derivative of the second part of that expression. So we'll go back here. And so the derivative of the first part is just going to be negative 2 times 200, which is negative 400. And then you multiply that by x to the minus 3 power. And then the derivative of this we did on the side just a second ago was that. Now, where I missed was I forgot to multiply by negative 2 here, so my numbers were off by about a factor of 2. Our domain is given the problem that x has to be greater than 1. We have to at least make 1, and we can't make negative units. So you set that equal to 0, first derivative equal to 0. And you see I can get rid of the 100 by dividing by 100 on both sides. Then what I do is I find a common denominator, so I just cross multiply these two. So you get negative 400 times x squared, x plus 30 quantity squared, and x cubed times 30, and then you divide by the product of those two. Now for a rational function to be 0, just the numerator is 0, so we can just ignore the denominator. And so that's what we get. We just take the numerator. So if we multiply this out, you'll get x squared plus, I think that's what I do here. So you use FOIL, x plus 30 times x plus 30 is x squared plus 60. So you take twice of that, and then you multiply these together, and you get 900. And then we multiply negative 400 times each one of those and regroup. So you got 30x cubed minus 400x squared, and then negative 400 times 60 is negative 2400 times x, and then you have negative 400 times positive 900. Gives you negative 360,000. And you know, you could factor this if you could factor it easily, but it's not easily factored. So what they suggest is using the root function of your graphing utility. So what I did instead was I used my graphing utility, and I'm going to share that with you. So let me go off of here. So I just plotted the function. And I have to use zoom out. So this is a plot of the first derivative, and so what we're looking for is when is the first derivative equal to 0. So it's right there when it crosses the x-axis. So I can zoom in easily, and I can see that the solution is 40.45. So that is the value of x, which will cause the numerator of our expression to go to 0. So we just write that down. So we get, well, that was the actual wrong answer. So we said it was 40.45. 40.45, and the actual equation was for hundreds, so we take that number and multiply by 100. So 40.45 times 100 is 4,045 units. So that will be the number of units to give us a minimum cost. So let's just go ahead and plot, you know, the original function and see what value of x gives us the minimum. So let me write that down. Well, I can just look at it in the book. So I'm going to go back here and sorry, I don't want to do that. Stop sharing. Start sharing. Let's go back and put the function in. So the original function was 100 times 200 divided by x squared plus x divided by x plus 30. And that's it. Okay, 100 times 200 divided by x squared x. Okay, graph. Okay, so there it is. I need to zoom out. I think maybe I'm going the wrong direction here. And there we go. And let's go zoom out in that direction. Okay, so you can see that you know, the costs are high initially, and then they come down, and they go through a minimum about right here. So you can see the graph is flat. It's hard to pick out exactly where that's happening, 37 up to 44. So that's why if you take this first derivative and set it equals 0, it's much easier to find out exactly where the cost is. But you can also see the cost doesn't matter. It's fairly invariant between these two. And then you can see it starts to go up again as we go greater than 40.